printer test.
This is the homemade printer. This is the computer. I've got my laptop over there, which I'm going to feed a program into to run the printer to demonstrate that. And this over here is the keyboard and readout display that's used to program the computer. This thing is a home design computer. It doesn't have any microprocessor in it. It's built more like a mini computer. So most of the circuitry here is actually what would normally be inside a microprocessor nowadays. So this is like mostly all the CPU here. The main oscillator on this thing is a 555 oscillator IC here, and it's got a potentiometer on here to control the speed. And the maximum speed this thing will run out on the clock is around a megahertz, and each instruction cycle takes 16 cycles of the oscillator. So it's around like actually 62,000 some instructions per second is what this thing runs at maximum, because of the partly because of the oscillator. And in this example here, I'm actually running the thing a lot slower than that, probably more like 60 instructions a second, or maybe even less than that. And I vary it with the potentiometer here. The computer was built with all wire wrap. This section over here is the arithmetic logic unit. This is a thing called a word assembler, special processor for handling nibbles. And this part of it here is the bit processor, and that allows you to analyze individual bits, see if they're on or off in an 8-bit byte, and also turn them on or turn them off. And this part here is the word comparator, or byte comparator. Allows you to compare two 8-bit bytes, and it outputs a comparison relationship there, greater than, equal to, or less than, and also goes through some inverters so that the next part of the circuit here can see not greater than, not equal to, or not less than also. And the next part here is the branch control and jump. Actually, it's the branch control, and also has a circuit in here for generating pulses, which is used for incrementing and decrementing counters. And then the next section here is the main instruction decoder and cycle timing circuit, and this is part of that too. This is actually decoding a bunch of the select lines, determining what processor is being talked to and signals are being sent to, and which ports being sent to. This over in here is 15 sockets for parallel I/O ports, and underneath the keyboard is keyboard circuitry. And this area right in here is the program counter, and this is address latch 1, address latch 3, address latch 2, which is also loop counter 2, and loop counter 1. This one here acts as an index register, this whole section right in here, and allows you to sequence through a whole series of step through a whole series of addresses for your operations. Like if you're loading and or feeding out a bunch of information or loading data in, this is an important register. Latch 3 holds the upper 8-bit byte of your 16-bit address for when you're doing operations on moving data around. And address latch 1 holds the lower byte, and of course this guy holds the lower byte, but it can be incremented and decremented. And loop 1, all it does is act as a counter that you can set it to a particular number, read what it is, and increment it and decrement it, and that's all accessed on the data bus. Address bus is kind of running underneath here. Data bus is running through the middle here, and this over here is the this 1K of static RAM, which is what's in the machine. That's what I put in when I built it. It's capable of addressing up to 64K. The instruction set on this machine is unique because it's determined primarily by how the processor is designed and wired. And I have basically there's 4 modes of operation based on the type of instruction. You can have single byte instructions, which use the loop counter 2 as the source of the lower byte of the instruction, and address latch 3 as the source of the upper byte for where it's going to go get the data. And then you can have a 2-byte instruction, which has the instructions, the first byte, and the second byte is the actual lower byte of the address for the data that's being used by the instruction. And you can have a 2-byte instruction in which the second byte is not the address, it's actually the data, so that's an immediate data instruction. And you can have a 3-byte instruction that the second 2 bytes are the least significant byte of the address and the most significant byte of the address. So you have a complete address for where you're going to get the data for the instruction from. And the main decoder part of it, that part in here, decodes for controlling all the communications between the various processors that are on the bus. And then individual processors, like there's the arithmetic logic unit stuff, have their own instructions that you send to that particular unit to set it up for what it's going to do. So it's just a transfer of the instruction to the processor, and then transfer of the data, and then reading out what the result is. So there's multiple operations on there. Here's the instructions for the bit processor. So you can go in there and set bits and reset bits and analyze bits. And there's the instructions for the branch control and pulse source section. And there's the word assembler, which it doesn't do a lot. It takes in 2 bytes, and you can rearrange the nibbles any way you want to generate a result. And that's the main comparator. Of course, you just put in 2 numbers, and then the branch control takes a look at what the result is. Even though there's the 3 different modes and they use different number of bytes, all instruction cycles are 16 cycles of a clock. So all instructions take the same amount of time at a given clock rate. The main instruction decoder, there's its instructions, and the first nibble of the byte is a combination of mode and what it is, and then the second nibble is really picking a particular processor. So you can see those are all inputs to the processors, and these are all outputs. So you can see that first byte's also determining the output, if it's an output or an input. And then once again you're selecting the outputs of the various processors, which there's fewer outputs than inputs. And then down here there's another bank of instructions which have primarily to do with the all the parallel ports and the keyboard and readout ports. So that's outputs, and over here is inputs, keyboard, and then all the input ports. Okay, this is the keyboard and readout on the unit. It uses hexadecimal format of entering your instructions and reading your data out. It's got a nice little 2D display on there. Stop indicator. This light comes on whenever the thing's halted, waiting for you to put something in on the keyboard, which there's some special instructions for that. And the green light shows when you're running. This light shows you what position this switch is in, and this switch works the two different modes of the keyboard. So in this position, the keyboard has the functions that are written above the keys. So this one's continue, which is it halts for either on a stop or on a stop instruction, which is a 00, or if it halts on wanting to input data, after you type the data in, you hit the continue button and that freezes up to keep running again. This is the master reset switch, which puts your program counter back to 0, and the program counter is also used for loading data. This is read, which allows you to enable the memory to put its information on the data bus, and you can read it out up here. Write enables the output of the memory to go to the bus if you're in the read mode. Disables the output of the memory to go to the bus in this mode. This allows you to see the address that you're looking at, which currently it's at 00. This allows you to step through addresses. Going forward, you can see the addresses changing. This allows you to go backwards, decrement through the addresses. This switch here allows you to see what's on the data bus, which currently there's nothing on the data bus, so it's showing an FF. This is a little flaw. The converter in there that's generating that character, whenever it goes to an F, it gives you nothing on this particular display. It's a bad part of the chip after 30 years. If I enable the bus, you can see that there's something there, but that's just noise that happened to be in that memory location when I started it up. Then this is the halt button, which halts the running of the machine, and this is the run button. And the only buttons I didn't explain is this one here loads the data that you've got entered on this thing into the upper address byte, and this loads it into the lower address byte if you don't want to have to go through the whole thing by stepping it. If you want to jump to someplace far above. And so the procedure, when you flip this switch down, then you're entering data into a latch, and it's whatever the keys are marked on them. So it's like 0 through 3, 4, 7, 8B, C through F. And these are sort of like just extra keys and they're not really used. Yeah, this is the instruction that's going to be used here to load the program from the laptop. As an example, first instruction here is just doing a dummy write to a port that isn't being used actually, or a processor that's not being used. But its point is to set up the address latches to really set up the most significant byte of the address. And then the next thing here is loads the loop counter, which is going to be used as the index register, with the location where I want to start saving data to. And the next byte here, or instruction, is actually a single byte instruction. It reads the status in and stores the status byte from the serial port into location 20, the first point being pointed to by that. This then takes the status reading out of that location and sends it over to the bit processor. This is the bit processor instruction, 2 bytes here, which sets it up to analyze bit 0. Then this is setting up a branch instruction to branch if it's not set, so it's waiting for it to be set. And then this is actual branch or jump instruction, during which it checks that condition. If the condition's met, it's going to jump off to 5. If you look at that, it goes back here and it checks the status again. So this just sits in this loop, waiting for information to arrive at the serial port. Once it's got something, it falls through the loop when that bit is set, reads the data from the data port on the serial port, and when that's a single byte instruction, it automatically sticks it into the point being pointed to by the loop counter, the index register. And then we do a 20, which reads it out on the display so we can see what it actually did put in there, and then 2-byte instruction to set the branch condition to unconditional branch and increment the index register loop counter 2, so it's pointing at the next location in memory, and then it does an unconditional branch back to 5, where it's looking for the next, checking the status again to see if it's got another byte ready to be loaded, and that just sits in that loop indefinitely, and there's no real stop on it. I've got 2 0-0s at the end here in case it didn't jump, it would stop, but you stop it manually when you're done dumping program into it. Enable, go to right. Enable the keyboard. C3. So we got a C3 in there. Go to the next location. 0, 0. Okay. And that happens to be a 0, 0. And what that's doing is setting up the area of memory where it's going to dump stuff into. And I'm going to start dumping it into 0, 0, 20, where it's going to all go. Which actually it's 20 hexadecimal, not 20 decimal. Tells it to look at byte it just brought in from the status register on the UART function. And look at bit 0 to see if there's a byte ready. And this takes a look and sees if the byte is if the bit is a 1 or a 0. 0 is going to branch, this is the branch instruction, back to 5. We got 3C. So that 03 tells it to increment the index register to point to the next location. 4, the branch, and go back to 05, which is our main loop, to get the next character. And I always throw a couple of stops in here, just for fun. Now let's see if, oops, guess I messed that up. Accidentally wrote a 0, 0 in my first location. Okay, C3, 0, 0, 0, 0, 82, 20, 3D, 09, wait a minute, 0, 0, let's see, 0. Okay, so this is all set up now. It's going to take bytes in with the serial port and dump them in starting at location 0020 until I stop the program manually. So we'll reset back to 0. Ready to go on that guy. And then I'm going to bring up the program loader program on the laptop. Select my prayer routine, which I'm going to dump in here. And this guy can go to run. And this guy's running. That's the interface over there. Serial port goes over here to the laptop. You hit the download button. And now we're downloading. You can see the data coming in here as it's going out of there. And that's the bytes coming down from the laptop. And you see the little LED there is going on and off. That's the flow control, so that makes the laptop wait on the old computer until the old computer has grabbed the byte and loaded it in memory and is ready for the next one. So that's auto flow control serial port. So this saves a lot of time, because otherwise you'd have to do the process you just saw, typing all this big huge program in with the keyboard. Now I did have I still do, I have a Heathkit paper tape reader which did the same trick using paper tape. So you could punch out a tape and you could read a tape in. And I also had a deal on here where I've got split power supply, so that you could turn off the computer but you could leave the memory powered up if you didn't want to lose what was in memory while you had it turned off. Okay, nope, not yet. Thought that may have been the end. So yeah, that's okay. It just dumped in the last part. It says it's done over here. Okay, we don't need that anymore. This guy's ready to go. Just gotta halt it. And I'm gonna run the memory address up to 20, which is where I loaded the program into. So that's where we're sitting on that thing when I hit the run button. Now over here is the homemade printer. This was built for about $15. Of course, remember this is 1975-76 time frame when printers were usually a teletype, and teletypes were $4,000. So if you had anything to print stuff out, you considered yourself lucky. This was a little weekend project I did to make something. It doesn't work the greatest in the world, but it's kind of entertaining anyway. And it's got a wheel here, which I glued on a whole bunch of characters from an old printing set my parents got me when I was a kid. And that's this part here is the character wheel. Sort of like a daisy wheel, only they're oriented differently. And this is a flexible shaft here. It goes back to gear here, and there's a gear here, and this is driven by a Lead-X rotary solenoid. It acts like a stepper motor. And see over here, there's this cam here. Every time this guy goes around, this cam's going to make this switch whenever it goes through character 0. So that lets the computer know where the thing is to start with. And then every time it goes through there, hits that switch, it's going to reset a counter in the program of the computer so that it is back to being synchronized with the wheel going around, and then otherwise it just counts pulses to know what character it's at. And then this stepper motor here turns this roller, which advances the paper. And of course there's the paper roll here, goes through underneath. This solenoid down here, see, this is on a flexible shaft here. So whenever this thing energizes, it's going to whack the paper down, the printer head down against the paper and print the character. And that's pretty much what there is to it. This guy advances the characters, that guy lets you know where you're at, and it's a fairly simple device. Now you can see I've put the stamp pad, this is a inking pad, which goes on top of the character wheel here, and that provides the ink for the character wheel to print. Run.
power test.
Well, finally got it to work after 20 years of not being used. Used this machine up until about 1980, and used it for all kinds of experiments, and controlling and monitoring experiments, and for learning software techniques and kind of stuff. One of the different kind of things I did with it was actually had it controlling an HO train set. Had little barcodes on boxcars, and when a train went through, the thing would read the barcode and determine which way to set the switches. So that was a cute little exercise I did with it. I built a Model 2, which was a similar idea. It was well, almost had it fully operational, but not quite. Using the Minicomputer format, no microprocessor, had a 16-bit ALU instead of 8. Still had an 8-bit data bus, but it had some 16-bit processors in it. And same size memory addressing capability. Had a full-size keyboard and a 8 or 9 digit hexadecimal display, and then I was going to have a video option using a TV monitor. The majority of the video you've been watching was produced in 2003, so that's 19 years ago. Here it is in February of 2022. Still runs after 46 years. I've got it running a little program that's just counting, and I've got it running really, really slow, so you can see it on the display there. It's not just a blur. If I was designing this thing again, I would design it quite a bit differently, but there's probably 25 ICs I wouldn't have to have in there. But it's a fun way to get into designing computers, TTL ICs, and strangely enough, after all these years, since they came out in about 1965 or so, you can still get the parts. A lot of them are poles, but get into that and play with it and design little circuits using them, and get into one of these books, and you can get all the diagrams that are used in it and apply it and learn a lot about how binary digital computers actually operate by playing with that stuff. Watch for more videos. I'm going to be doing some more of these YouTubes on my Steve Fry Tech channel, and hopefully you'll enjoy them. Let me know.